lassen, dass ich nicht weiß, wie viel ist 100%ig ab. Und dann
Oh no.
Liegt da eigentlich auf der Seite, das halt das Video nachher.
Okay, a warm welcome being here. Thank you for being here. On Tuesday, we started with the timing analysis methodology. I kind of repeated the constraints that constrain the maximum possible clock frequency. That's where you're working like mostly at. I introduced this idea of an arrival time and the required time when the signal has to be there, and the idea of slack. I showed that this is working in FPGA, or I repeated the SDC files on basically two, or let's say three things which cover already quite a lot in timing constraining. So creating a clock, setting an input delay, setting an output delay. I showed that setting an output delay will introduce a kind of virtual flip-flop plus some logic that is in front of the D input of this virtual flip-flop, and hereby constraining the output paths to primary outputs, and an input delay which will constrain input paths from primary inputs to D flip-flops with the same idea. So that's the idea how you tell the EDA software what you want to do. At which clock frequency do you want to run? 90% already covered by that. And then primary inputs and primary outputs in a synchronous manner. I showed that all with the example of this circuitry here, which is composed of a counter and then some logic that counts the number of ones in a 48-bit vector, and when there are more than 24 ones, then one bit will be 1, otherwise it will be 0. So that's the combinational logic cloud here in the middle. And I showed that when you run this with 50 megahertz, then you can have this nice picture here showing that this works, and you still have a slack of 7.6 nanoseconds when you have a clock period of 20 nanoseconds, so 50 megahertz. But when you increase clock frequency, then you miss that, so you don't have 20 nanoseconds, now you just 10 nanoseconds, but you miss it by 2.5 nanoseconds this period. So you can't run this with 100 megahertz, at least under worst case conditions. But yeah, I then showed an idea of how you can change that or tackle that on RTL level. I also mentioned that this is a much bigger lever than anything you can do on the gate level netlist. So this is normally the place where you should first look at if you think you have timing problems. And one idea is introducing a pipeline register with the idea to cut the logic cloud, hopefully somewhere in the middle, and add a register there, because then you have a path from here to something here in the middle, and the second one starting here, ending up at the end. And if everything works nicely, then you probably have split the logic delay between left and the right side of your pipelining register. And the impact of that is on RTL level, you will have the result 1 clock cycle later, and you have to decide on whether that's a problem or not. You can only decide that on system level, whether that is acceptable or not. But this is a part of your toolbox, what you have. Anyway, it turns out this works. We have 1.35 nanoseconds slack, so we can run at 100 and maybe even a bit faster. We have now 100 million samples per second throughput for our circuitry. So if that's the thing that you need and latency doesn't matter, then it's okay. Squeezing it a little bit more, we can run at 116, then the slack is only 59 left, 59 picoseconds left. So that's probably the end of what you can do here. And a short visit on the counter. If I just look at that one, we can run the 48-bit counter at 166 megahertz. That somehow is in the order that they claim in the data sheet on how fast can you run things there. So this is some intro in the timing analysis, and I added some questions here at the end of the PDK. Whether you could analyze that for the counter design, so figuring that out, it will turn out this is so small, it's limited in your output or input path, I don't remember. So you could add additional registers at the primary input and primary output so that we can focus a little bit more on the counter core itself. That is something you can look at. So what happens when you increase the counter width? What is the maximum frequency for several bit width? The counter is not running that long, so you could easily figure that out. Before doing that, I want to dig a little bit deeper into this timing analysis topic, and that is chapter 8 from this book. I added that in the list on the wiki, and today I want to look at this chapter 8. We only had this one inverter, how you calculate that. Then we saw the big result on the FPGA where you have lots of parts, and I want to give a glimpse on how is this done in the software. So how do they handle that? That's here, chapter 8, so that's more or less at the pretty late. That what I want to look at is static timing analysis and maybe delay budgeting. But first thing is static timing analysis. How can that be done? And how can you figure out what are your critical paths? How is that done in software? So in his book, he puts that into this last chapter, so it's already after routing and placement and clock tree analysis. The truth is that you need the timing analysis also during placement and routing, because otherwise you can't do a good placement and can't do a good routing. So it has to somehow work together. So it's not useless to know that. Placing cells just by, so one other constraint for placement would be that it is actually routable. So how do you place it that your wire length is not becoming too long, and it should not be too much area, of course. So other constraints, area, routability, but in the end you must achieve timing closure. That's what you normally work on. That's a hard thing. So mentioned here timing constraints, that what I introduced. I looked only at the setup constraint, which is limiting your maximum clock frequency. But you have one other constraint, and that is the hold timing. So you must have something that will avoid that your signal is changing too fast at your output of the flip-flop, because then you have a hold violation that is something on top. But it turns out you're normally working much more on this here, and hold time violations can be fixed by introducing delay, which is normally not that complicated to introduce delay. And this, to achieve these timing constraints, that's called timing closure, to achieve your speed requirements. And as mentioned here, this is actually working in all those steps here. So you have timing-driven placement, timing-driven routing, and then you can couple that even more. That's called physical synthesis, where you want to always also look at timing requirements for placing and routing. So which paths or which routes can be very long because they are not timing critical, which wires need a very short path, which cells have to be close together so that you achieve a short delay. This can only be derived from the circuit and your timing requirements. So we did that already here, what was set up and hold violations, timing closure, and so we had a look at that in the previous slides. So that's what we know already, the combination of cloud with flip-flops in between. What was skipped in the previous slides is that we have gate delays, but also wire delays. So I had no wire delays in the inverter, but we saw from looking at the PDK that the wire introduces a capacitive load. It will change timing, so you can also say that the wire has a delay, so the wire delays. And what was ignored is clock skew, so your clock will arrive at different times. So that is what you want to do, and the tool to do that is static timing analysis. So how does that work? The first thing is we assume that every gate in the circuit works under worst case conditions. So we always want to figure out what is the latest possible, not the fast best case scenario, so but the latest possible. The idea, and here this is kind of connecting it to algorithms and software, is how do you represent the circuit in software, in EDA software, so that you can do this analysis. And the idea is to represent that as a graph and then each wait is a wire or gate delay, and so it's a weighted graph, and you have these ideas here of required arrival time, the required time, and the actual arrival time. This is what I call arrival time and required arrival time, so RAT and AT, and that is the slack, so we introduced that already. And as in the FPGA, if you have negative slack, you have timing violation, so it should not be negative. Positive means it's good. So, and what you do is you have a circuit, an example circuit here, a short, small circuit, and this represents here primary inputs are here, the output is here, then you have here numbers which are related to the gates. This here is the gate delay, and this here is the wire delay. And you transform that to such a graph. They always like graphs because this is something they know how to handle that in software, how you can represent that with data structures. So you transform, you say you have a starting point where you say this is now the thing where it starts. And then you say, okay, I have A, B, and C, these are my inputs, and what this means is here you have already a delay at the input, meaning the signal will arrive at C a little bit later after your common start point. The common start point translates into the clock edge normally. So you say, okay, this input A and input B, they will immediately start, but C will start only 600 picoseconds later. So then comes the wire delay, that's represented by these edges here, and then you have here the nodes where you have the gate delay added. So this is just transforming it. This is here. This here is new. But the remainder here is the output. That's just the output. Okay, and the method for the static timing analysis is this rule here. The AAT, so the actual arrival time at one node, is the maximum of the actual arrival times of all nodes U. So this is the fan-in of that, so U element of the fan-in of V. So you look at all inputs of your circuit, and then you take the arrival time of all the input nodes plus the wire delay from that input to your node, and from that you take your maximum. So what does that mean? Maybe something simple and stupid at first hand. So you start here on the left part. You say, okay, when this starts, this is an arrival time of 0 by definition, because the start is at time 0. Then it takes 0 time to end up at the input of the circuit. So the arrival time at the input is also 0. The input doesn't add any gate delay. So the input time here is 0.15 nanoseconds at the Y2, and that was this gate here. So it takes 150 picoseconds to arrive at this input. Here, the input B arrival is also 0, but at C we arrive at 600 picoseconds after start. Now we have this inverter. See, in the middle. This inverter has a fan out of 2, so you have a wire delay of 100 picoseconds to this AND gate and a wire delay of 300 picoseconds to this OR gate here. So this is the X node here, a gate delay of 1 nanosecond. So let's look and evaluate this function for this case here. So Y2. Y2 has a fan-in of 2, so we have 2 fan-ins. And this procedure here means we look at every input and check what our time is there. The first input is here from this primary input that starts at 0 and has a wire delay of 150 picoseconds. And the gate delay of the whole thing will be 2 nanoseconds. So the timing arc from here to here will be 2.15 nanoseconds if this input here changes. The other input has here an arrival time of 1.1 nanoseconds. That comes from this input B. It has 100 picoseconds wire delay, and then the inverter has 1 nanosecond. So at the output of the inverter, we arrive at 1.1 nanoseconds. Then that's this one, 1.1 plus 0.1, that's the time here. And that is the 1.2 adding 2 to it for the gate delay, and then we have 3.2 at the output of this NAND gate. So we basically reduce it to the signal that arrives latest at our gate. Here we still have not modeled that, as in the Liberty file, that every input has a different timing arc to the output, but you could add that. Here it's just the wire delay. So we end up latest at 3.2 nanoseconds at the output of that gate. And we do that for all gates. And of course, in order to have the 1.1 here, you have to start from left to right to develop this thing. So here, for the other gate, we start at 0. The input C, there it arrives at 600 picoseconds. We add 100, so that's 700 plus 2 will be 2.7 nanoseconds here for that gate. But here we arrive much later, 1.1 plus 0.3 is 1.4 plus the 2 is 3.4 nanoseconds for that node. So with that, we finally end up, we do the same here. So here we start at 3.4, here at 3.2, 3.4 plus this is the longer path, so 3.4 plus 0.25 plus 2, that's the 565, where it arrives here. Then we have the wire delay, and at the output we end up at 5.85 nanoseconds. So this method, if you think about it, you think, yeah, this is obvious, whatever. But when you think about it, it's already quite an idea to do it that way, because you don't look at previously. What people did was they had such a graph. They made a list of all paths through this graph. So this path and this path and this path and this path. And then they looked at every path and checked what will be our time through that path. But the number of paths will increase dramatically with the size of the circuit. With this algorithm, you stop looking at a path when you have another path which will arrive later. So you kind of kick out this path here from anything that's going further. So here, from here on, this path is ignored for the following part, because the only thing you want to know in the end is what is your latest arrival time on your circuit. So that's how they do it. The required time is working like differently. I showed that in the timing analysis report from the FPGA, where they said, yeah, the requirement at the end is my clock when the receiving flip-flop is clocked, and the setup delay. That is my required time. But you can, so this one is given from your flip-flop basically. And then you can take the graph here is basically the same, except that you choose here the minimum times that you have. In this example, the times here don't change, so they are static for the purpose of this example. But now you want to figure out what is your required time that you need, and you want to add that to each node when should the signal arrive there. And for that, you look at the fan-out of your design, and you reduce your time. So you want to, you must arrive. It's your required time, 5.5 nanoseconds after the clock edge. That means, going back to the so you know that you must be here 5.5 nanoseconds after the rising clock edge, but that means you must be 200 picoseconds earlier at the output of the gate, because the wire will add 200 picoseconds. So this drives this, so from here to here we have the 200 picoseconds, so we must arrive at 5.3 here, and now we can look at this one. So here we have 5.3 minus 2, that's the gate delay. So that's 3.3 minus 2 is 0.1, 3.1. So that's the required time when the output of this gate must be stable. And same here. And probably the interesting thing is here. So this gate, the required time of 0.75. Can you explain with your neighbor why there is 0.75 for the X gate here, this one. So you talk with your neighbor, or you first think and then talk, and then explain why it says 0.75 for this inverter.
Ja, dann war's nicht. I see what you mean. You do? How are you going backwards? I know what he's saying. How do you dash it down? How do you move back?
Und alles klar? Unter Punkt 7 it's obvious why there is 0.75. No, wait, 0.75 here. Point 0.75. It's obvious.
It's just the go 3.5. How are you going backwards in time?
Yeah. And why don't you go that part? I mean, you could also go to this part. Yeah, on this Why 0.75? Yeah, why should you take that?
It's funny, I was about to say that there's which is there for the moment.
Take one here, then you arrive too late, this will.
Okay, so walking a little bit around, I think everybody figured out that 0.75 can be computed by taking 3.05, subtracting 2, ending at 2.05, subtracting 0.3 will result at 0.75. So that's how you mathematically compute 0.75 from all the numbers which are here in the graph. So the question is, why is it this path and not that path that you take? Because you could do the same way of computations, you would end up at a different number. So you would here have 3.1 is the required time at the output of this gate. You subtract 2, that's 1.1. You subtract 0.1 and you end up at 1. So your required time would be 1 nanosecond and not 0.75 nanoseconds. So the question is, why do you take this one and not that one? And for that, to achieve the required time here, you must have the strongest path, so to say. The critical path will dictate that you achieve the required time here. This one will be more optimistic if you pass that way. So that's why you have to take the minimum. I mean, it's mentioned here that you have to take the minimum, but the reason is you want to achieve your required time at the end. So that was the critical thing. So from that you can compute back, and you could say, okay, it would be still okay, 0.35 required time is so to say negative. So now you can compute the slacks at every node. We did that for this inverter example. So our required time is 5.5, our arrival time is 5.85. If you subtract that, you get a negative slack. Negative slack is like bad because you are arriving later than what is required, and that translates to a required time which is before your start time. So you could also start earlier, then it would be okay, but you have a negative slack at this place here. So hereby you translate the slack at the end to like all the intermediate nodes, and you can see where it's already negative. So you have an arrival time of 1.1 here. It should be there at 0.75. So you are screwed up. You're screwed up in all those places. So that is what the static timing analysis can do. Normally for us it would be okay to figure out, yeah, okay, we have the negative slack here at the end, it's not good. But when you want to figure out where is it actually making problems, you can work backwards from that thing and figure out what is the critical path that drives that makes it difficult to achieve this timing. So that is an algorithm for doing timing analysis, and this way of doing it is completely different from you take the gate delays, you take the wire delays, you put that in a simulator and you simulate your function, and then you have checkers which check whether you have setup and hold violations at all flip-flops, which give an alarm if there is a violation, and if your delay is so bad that you end up 1 clock later, there will be a functional difference, and hereby you could check whether your timing is okay. That's the methodology from like the 70s or 80s, where you tried to back annotate all your timings, run the simulation, and see whether it's still working. This method for static timing analysis makes no assumption about the function of the circuitry. It doesn't matter. You take the netlist, you don't need to know what it actually does. You just see the structure. You don't need to figure out how does this, what is the value of nodes. So is there a 1 or a 0? You don't care. The only thing you do is caring that when there is a transition at the input, how does this travel through the gates. That's why it's called static, because you don't need any dynamic simulation to check it out. You just look at the static behavior of the circuit. No stimuli needed, no nothing. So that's one method or the method for timing analysis. Yeah, let's leave it there for the moment. If you do that in reality, then you do you make the model more complicated by trying to differ between rising and falling edges, because that might have different delay times, and you get a very pessimistic assumption or idea of what the required timings are if you ignore that. One simple one simple example is this here. You have an inverter chain and you check 1 nanosecond TP. You have a propagation delay for a low-high transition at the output of 1 nanosecond. You have a propagation delay of 2 nanoseconds for a high-low transition. If you are supposed to estimate your actual arrival time under worst-case conditions, you would assign the worst case of that. So meaning you say, okay, worst case, every inverter will have a delay of 2 nanoseconds, because you don't know anything about whether it's going from 1 to 0 or from 0 to 1. You don't look into that. So you would assign 2 nanoseconds for each and every for each inverter, and then you would get an AAT at the end of 6 nanoseconds, and that would be your estimation for the delay. But when you look at the structure, you know there cannot be, this would only be the case if all inverters would have a transition from high to low at the output. But this is not possible because this is an inverted chain, so there must be 2 different from the other ones. Yeah? So you cannot have this transition. And it turns out you can integrate this into the timing analysis. So your worst thing that you have in reality would be that you have here 2, 2, 1. That's the only possible way, the worst thing. You would be too optimistic saying, yeah, it's 1, 2, 1, that would be lower, but it could be opposite. And there is a method to include this by adding this notion that we saw in the Liberty file, that the gate is positive innate or negative innate. So when we have a rising transition at the input, then we will have rising transition at the output. This is true for OR gates, AND gates. For them it's true. For inverters, they are negative innate. And you can include that into the static timing analysis, because when you include that, you will figure out that your AAT is 5 nanoseconds in worst case. It will never be later than that. And this shows that by, changing the algorithm and adapting it and making it smarter, you can make a timing verification which tells you can run faster. You have not changed anything in the circuitry. You only made a smarter algorithm which tells you, you have 1 nanosecond more time, meaning you can increase clock period by that amount without doing anything. So that's an example for, I put 1 more in, and static timing analysis will be correct, but it might be too pessimistic. Maybe it works faster, but you have a guarantee when you do this STA analysis, the static timing analysis, it will run at that frequency that you have proven. It will be there. Maybe faster, but in any case, it runs at that speed. And adding more smartness into the algorithm, that's what's in there today. So you add rising and falling transitions, you get better estimations of your times. Okay, there is the next thing here in the slides, or in chapter 8 from Kang, and that is the relation of the static timing analysis to placement and routing, because what he wants to figure out is if I have such a circuit and I have, where was it? Yeah, okay. Here in this example, you have nothing. So the question that he wants to solve, or that he looks at in the next step, is you have here a circuit which has done static timing analysis. Here you have the notion of the arrival time, the slack, and your received, your required arrival time. And you see that you have slack here at all those places. The question that he wants to solve is, okay, there is some margin in the circuit. Which wires can be longer? Which gates can be slower? Where are my options for placement and routing? Which cell can I move further down? Which need to be closer together? I mean, we know from static timing that, okay, this is our critical path. So we could say, this is the critical path. We look at this path and make this really, really fast. But maybe by doing that, we kick away our second worst path, and that will then be violated. How can you get an idea, okay, this gate can move further away, I can make it worse, but this, I have no margin at this gate. We know that we have slacks, so there is some possibility, but how can we assign this to individual nets and gates? Is there a way? And that's the zero slack algorithm, with the idea to assign a timing budget that is assigned to every wire or every gate, so that we know, okay, we can move this gate this far until we end up in a timing violation. But we'll not do this today. Today we'll look at the timing of the counter. So you can run the counter, and we do the stuff mentioned last time. Here, what is the critical path in the counter? You add primary input, primary output registers, and just do it. And look at the counter design. Everybody knows how to add the registers at the inputs and outputs? But maybe you can first have a look just at the pure counter design. This. So Speed?
It's too much speed.
It's too much. It's running hard.
I crashed.
What crash? You have the VM?
Yeah, that's what they're doing.
The VM?
Yeah.
You have a PC?
Yeah, yeah.
In
I
here?
haven't got the counter set up yet though.
Hmm?
I haven't got the counter set up yet though.
The count? But that was there already.
No, kind of.
Hmm?
Which counter are you talking about?
The counter
In
example.
Open Road?
Yeah.
Yeah, I don't have that yet.
You then why not?
Because I've been playing catch up.
Mm-hmm.
I'm struggling with another module at the minute, so I've been putting more time towards that. So
Okay.
I'm playing catch up at the minute.
Okay.
Like I told you last week.
Any results what the critical path is?
I don't know.
Huh?
Is this one? Design. Oh, I'm in the wrong folder.
Yeah, but yeah, that's all good look like.
So maybe one step doing that is making a small sketch of the circuitry on paper. So how does this VHDL code, if you would draw that on paper, how would that look like? Kind of block diagram.
Where are we meant to be off these registers?
Okay, drawing a block diagram of the counter to sketch a little bit where the ports are. So here's our entity that tells us what the inputs and outputs are. So and enable in, we have the clock input and we have a reset input. And on the output side, we have the count O. This is currently 15 down to 0. So 16 wires, ports at the output. Now we have to interpret this SQL code and make a drawing out of it. What this looks like. So what does it say? It says count should be all 0 when the reset is active, meaning we will introduce a register which has 16 bits and it has a low active reset. The output of that is called count. And the input of that is not explicitly here. It says if we have no reset, and now I move then it should be count plus 1 when the enable is 1 and we have a rising edge on the clock. This translates to here an adder. We have here a count signal. Here we have 16 lines. Here is an enable. And if I would just, connect it like this, then I would ignore this enable thing here. That would be just a counter. But I have this enable in there, and that introduces such a mux and this mux is connected here to this enable signal, and this is our circuitry. And now we have the clock that's attached to the clock, and now we have the last line here that connects the counter output to my input count signal. So that's the last line of code. So this is our block diagram of the counter. When the enable is 0, we load the count signal again. When enable is 1, we increment it by 1. There would be an equivalent description that would be identical. I think that's the way how you do it. That would be introducing this next count, and that's an alternative how to do it. So we change this here. This is the classic register description, and now we put the next state logic in one is count plus 1 when enable y is 1, and else it's count. So this is the same functionality. Now I have next count explicit. So this would be then next count. Next count is the D input of the register. So this is our structure. Taking this structure, running the synthesis, where is the block in this design? Not looking, there's no way to just look at the block diagram. You need to run the synthesis. Run the synthesis. So to run the synthesis, you have to uncomment here design configuration for the counter. Then go into this flow directory and then run make. Final, and you will see the design.
Kan jeg lave det? I så kan jeg lave det? That's not make GUI.
Oh yeah, make GUI final.
Yeah.
Yeah. That's not too bad.
Yeah, I missed that. Longest time I have no idea how to get that up.
Oh. Okay.
Did that run?
I need to put the code in, but my keyboard was stuck in the German one, so I'll have to do it after. But I had to change it to the UK.
But for what?
The keyboard's wrong.
My keyboard was in the wrong one, so I didn't get it done in time. But I'll do it in a minute after class.
Does it work for you?
Did you get a photo of the code? No, I can type it in.
Let's see.
That's why it would be handy to have two phones.
Don't know if I got the stuff that he changed, but I have that.
No, I need the next count.
Right.
You can have just come on and then next day. I think I have it here. Just a second.
There we go. Now I can have this. Save. And I need to open the make file. Blue. Where is that again? Hello. Hello. And then you gotta wait. Yeah.
Do you remember how to get off the German keyboard?
Oh, it's not in the German keyboard anyway.
Okay, when you run the synthesis,
That's just one of the things that doesn't change properly.
and have it all up and running, then I look here at the timing report window. That's this one, and as now done for a couple of times, you can here. These are all the paths which are sorted by Slack. So your worst path is this one, and then the next one. These are all the paths which are critical here, listed in criticality order, so to say. When you do that, so what I made, I did the nets, I switched them all off. When you have this all on, then there is sort of the
No,
routing
you
and
could've
the
just
power
made-
supply. I switched this all
I
off.
can't remember what the previous command is. There's one before this one.
Instances. Yeah, you can add the instances here
Stop.
and
What's
see
the
just
command
the,
before? Make
just
GUI
the
file.
cells. But you can, I switched off the physical ones and also just the cells which are there to connect all the power lines, but they have no function, so I switched them off. Pads, there are no pads. Macros, there are no macros. So I have this view where only the place cells are there, and then you have this timing path here, and it has different components. So when you select something here, then you see the capture clock, the data path, and the
That's what
launch
make
clock,
file is.
and the
You have to do
legend.
with
So
the
I
make
can
file.
switch off the legend here. That's obvious. but I think in your version this is not colored, but you can, just switch off everything except the data path. The data path is that starting somewhere, ending somewhere, and it should end here. Let's see, X or here is the last thing where it ends. So this is the is a flip-flop. Of course, it should end at the flip-flop finally, and that's what you can see. The data comes in. We can see the capture clock. So that's the clock that clocks this flip-flop. You can see that the clock is here. The D input is here, and that's the path where it arrives at the flip-flop here, the last thing before you enter the flip-flop. So these are the sections. Here's an XOR gate, a NOR gate, a NOR gate. Here a buffer, another buffer, an AND gate, another buffer that's not visible now, so you can walk through that. And the interesting thing is that it starts, let's see here, this starts at the primary input, at the enable input, where it says we have 2 nanoseconds. That's our, let's say the virtual delay is 2 nanoseconds after the clock edge. So we said it will be clocked with our 50 megahertz clock. That's the core clock. But it starts at the enable input, so there is no real register where it starts at the primary input. So we have a critical path that somehow goes through the enable input and ends up here. Obviously there is no, is there a multiplexer here? No, this is just gates, because this is all put together. The incrementer, the multiplexer that's replaced by some logic, and these are all the gates where it goes through, where it travels. So that is the critical path at the moment. The arrival time is 2.9 nanoseconds after start. Required time is 10, so we have really a huge slack here. The logic delay is just 600. That is the delay from these gates here. The logic depth of 4, but this is the critical path at the moment. So if we want to look more at the inputs, and we see this enable signal, that's here the critical thing, then the first idea would be to add a flip-flop just in this line. So flip-flop here, so that our 2 nanoseconds input delay, which comes just by definition, will be consumed by the first flip-flop, and then the remaining part is the internal logic. How do we change the VHDL code to get rid of that? So we want to introduce something like this. We have here an additional flip-flop. The enable input goes here, and we have a signal called enable, and this is connected to the clock, and if you want also do the asynchronous reset. So how do we need to change the code to have that pipeline register introduced?
Oh, you have to run just make first to compile it.
Make and then make GUI final.
Oh, this is like this, like,
Yeah.
So, what I'll do is I'll introduce this additional net here. I do that with this. This introduces the internal enable net. And the enable net is something that is driven by a flip-flop. So this introduces the one flip-flop. And to make it now active, we have to replace this. Let's see. Okay, now the critical path has changed. We have a required time of 8, and if we look at the timing path and look at data, so this is obviously something going maybe out or in. If we try to set the launch clock, we see it, but the capture clock, there is no capture clock because this is now a path to the output. So we start at a flip-flop, the count O, so the count flip-flop, and the output is count O 12. So this is only clock outputs. Now we just go over 2 buffers to the output. So this is a logic delay of 200 picoseconds. So that's more or less not a lot. But this is currently our critical path. And what can we do now? Because this is already a flip-flop output. There should be no logic in between here. there are only 2 buffers. Those 2 buffers, so the fan out here introduces 200 picosecond, 235 picoseconds delay. There is a fan out of 5, so some flip-flops attached to it, but there is a buffer introduced, which adds here a small portion, but this is really not a lot yet. Yeah? So what could we do to have a focus more on the internal speed of the counter? The first thing we could do is decouple it by adding now an output flip-flop like we did for the input. We can do that, and then we can change the timing constraints, because we have 2 nanoseconds at inputs and outputs, and obviously the 2 nanoseconds are a lot compared to the internal delays for this 16-bit counter. Yeah? So we can add another one here, and then use the timing constraining to have a focus on the internal parts. Okay, so there's a little bit more to do. Thanks for your attention, your interest. See you next week, and wish you a nice 1st May. You on the market with your red flags. Yeah, red flags. Okay, see you next week.